Yeah, good. So you only need to
This meeting is being recorded.
Is a sound?
connected to the speakers. Do we need the microphone?
Okay.
Let's hope we can do it tomorrow.
And is there a pointer? I don't know.
It's better to use your cursor if
Yeah,
possible,
okay.
because otherwise online people won't be
Sure.
able to see it. So you need to blow up your cursor a little bit if you know how to do it.
I don't
Oh,
know how to
actually,
do it.
Are
I'm
you
not
on?
sure. Yeah, I can try to. Okay, without mouse, it will be difficult anyway. I will.
Yeah. Okay. You are on PowerPoint or
It's a PDF.
PDF.
So-
Okay. So then, yeah. Okay. Let's start. Or you can change the cursor on the computer. In Mac,
Yeah.
I don't know about.
Okay, then. Thank you to the organizers for allowing me to talk here today. I will present an ongoing project which I started recently with James LeBlanc at Memorial University, and in which we use a numerical technique, algorithmic Matsubara integration, to study the optical conductivity in the Hubbard model. And I want to mention also the contribution of some people here in King's College in London and from University of Massachusetts that helped develop all the machinery that is behind all the results I will show you today. So I'll start by introducing algorithmic Matsubara integration in a very simple way, starting with a very simple calculation, for example, of this diagram, just particle hole bubble. And following the usual Feynman rules, I can give an expression to this diagram. And as I think everyone here knows, we can get rid of the Matsubara sum using simple residue theorem if we have three fermions. And we have this expression, which is just a Linhart function, where we are left with a d-dimensional integral. So the result will depend on the dimensionality of the problem. And we have our external frequency that we can continue on the real axis by using the usual analytic continuation. And this is a very easy and general setup, but it becomes much more complicated to use if we, for example, want to compute an arbitrary self-energy diagram. So here I have a ninth order diagram in which I don't think we can anyone can give an expression, but there is still a structure that we can use. In particular, we know that this diagram will have an expression in terms of product of more than 9, 12 or Green's function, and that we can still get rid of the Matsubara sum using residue theorem multiple times. And we get a result where we have 9 times d-dimensional integrals for the internal momentum, and the external frequency appears in the denominator with some function of the dispersion, but we can still use analytic continuation to, if we want, compute result on the real frequency axis. So now, of course, there are other techniques that allow us to evaluate such a diagrammatic series. In particular, diagrammatic Monte Carlo is a very popular one. But because this technique actually stops at this stage and evaluate this integrand here, they are restricted to computation on the imaginary time or imaginary frequency axis, and which is, then they need to use some numerical analytic continuation tools to get results that they can compare to experiments or others. So the idea of algorithmic Matsubara integration is really to use these simple rules that we know and that we can implement to get this analytical expression that we then integrate numerically. So the scheme is very simple. We will generate all the diagrams for a quantity that we want to compute. And we will also assign all the momentum respecting the conservation laws for momentum, spin, or energy, and so on, depending on our interaction. And then we use residue theorem iteratively to get an analytical expression for all the diagrams we started with. And we are left with an integrand that only depends on internal momentum and some external parameters such as temperature or chemical potential that we will integrate numerically. And it turns out that even for large order diagrams, the numerical integration is the more costly part of this whole process. So of course, because of the high dimensional integration space when we have a lot of internal momentum, and because of the number of diagrams, this last step is the one which will cost more computation time. And this whole process of generating analytical expression for the integrand is actually very quick. Another, just a quickly, advantage to this scheme compared to the standard diagrammatic Monte Carlo is that if you have a interaction that's not dependent on momentum, it only acts as a prefactor in front of some coefficient that is given by the sum of diagrams at a given order. So you can actually evaluate, for example, once again here, the self-energy for any value of the interaction in a single calculation of these parameters. So this technique is general, and we can use it to any diagrammatic expansion in principle, but I will here focus on the Hubbard model. And even more restrictive, I will focus on the 2D Hubbard model at half filling for everything that is left after that. And because I'm dealing with diagrammatic expansion, I just here give the interaction vertices that we will use. And all the energy scales and everything will be given in unit of t, the hopping parameter, which will be taken to 1. So now what could we compute with this AMI technique? Every quantities I can think of, at least. For example, the self-energy is maybe one of the first one can think to compute, and it has been done, for example, up to 6th order using AMI. Also, two particle quantities, so that the charge, spin, or pairing susceptibilities can be computed. And once again, it has been done to 4th order for the charge and spin susceptibility, even away from half filling and in some with some t prime parameters. And what I will be interested in here is the current correlation function, because it relates directly to the optical conductivity. So to study the optical conductivity, we'll use Kubo formula and not the Boltzmann equation that was presented just before. So in this sense, for us, in this linear response theory, the conductivity is just given by the current correlation function divided by the frequency with some imaginary factor, which means that if we want the real part of the conductivity, we will need to focus on the imaginary part of the correlation function. And this is the correlation function that we will expand in a diagrammatic series. Actually, it's this current here, average of the current operators that we will expand. And if you do this, you can, write down all the diagrams. Here I stop at 2nd order. You will find that for free fermions, the Lienhardt function here vanishes because we have taken a Q going to 0 limit. Same for this second diagram. And the first non-zero terms will come from this 2nd order diagrams. But if you actually evaluate them,
could you repeat it? This was too quick. Why don't we need the first diagram?
So if you have free fermions,
yeah,
then this will vanish because we have a Q equals 0 incoming momentum, and then for finite frequency you have K and K on both fermionic lines, and this will vanish. The numerator will vanish if you write on the.
It's a scary 0, right?
For finite frequency, it's.
Oh, you're at finite frequency.
Got
it. Yes, of course. At finite frequency and Q equals 0, that's perfectly fine.
Yes, I will mention the DC limit of the 0 frequency case a bit later. So I don't focus on this right now, but.
I'm always.
So if you evaluate this second order diagram that I had before, you will find that because you still have analytic contribution parameters here, your result will depend strongly on these parameters. And you can even see if you rescale a bit your axis that it is the only thing that controls the low frequency behavior of your results. And one of the consequences, for example, is that at second order, the calculation that I've done here, conductivity will diverge. And also depends on the non-physical parameters, which is this gamma here. If you look more closely at what happens in this calculation, you will find that the dominant contribution actually comes from the self-energy inclusion in the diagrams, so diagrams of this type. And this is why we actually use the idea of bold diagrammatics.
In the previous slide,
yes.
The limit omega to 0, does it commute with gamma to 0? Because I know that when you're using the Kubo formalism and working in the math gauge, for example, you can find some problems whenever you take Q to 0 and then omega to 0 or reversed.
So do you mean Q or gamma? Because you said gamma.
Ah, sorry, Q to 0, yeah.
Yeah, so as I say, Q to 0, then the two limits are not the same. So here we need to take the Q to 0 limit first, and then if you want to study the DC case, we need to take the omega going to 0 limit.
Okay, so you start from the gamma to 0 and then you take omega to 0 first.
So okay, here gamma is a small imaginary part to the frequency, so it's not the external momentum, right?
Yeah. Yes, I mean, I'm wondering if we find any troubles in the computation of these two limits, omega to 0 and gamma to 0.
Actually, I have not done it because I don't expect.
Well, I mean, it must, right?
Yes.
If it depends on only on omega over gamma,
Yes.
it is important whether you look at infinity or 0,
Yes.
right? Which is.
But okay, all of this was actually just to motivate what we do next. So I have not looked exactly at, as you mentioned, the gamma going to 0 limit. Also because if the computation was well behaved, because this is finite temperature computation anyway, so if the computation was well behaved, I would expect that once gamma is much lower than all the other energy scales, which are like temperatures and so on, I should get a proper answer which do not depend on gamma. So I don't think I did not like looked into this gamma really going to 0, right?
Some other limits when computing this subsequent conductivity, you can run into some serious problems whether the limits come in or not. So
Yes.
perhaps it's worth checking.
But anyway, here I am actually not taking any of these limits. I'm not looking at the omega going to 0 limit, and I'm not looking at the gamma going to 0 limit. So the idea was then to use the idea of bold diagrammatics, so where we can actually renormalize our electronic Green's function by including some self-energy correction. So here, an example where we truncate the series at second order. And because these diagrams has a finite imaginary part, it will regulate computation. And in this case, the current correlation is then given by what we call the skeleton series, which is the same as previously, but where we removed the self-energy inclusion to avoid the double counting and so on. And now this first diagram, the zeroth order diagram, which now includes a full Green's function here, actually have a finite value. But because the self-energy itself is momentum and frequency dependent, within the AMI scheme that I described previously, it's difficult. So we use just a spectral representation for the Green's function by introducing the spectral function, which is a smooth and well-behaved function. And we now get a pole structure that is very similar to a non-interacting problem that can be dealt with with the AMI at the cost of having some extra integration variables.
So you keep those extra integration variables over real frequencies if you want so, and then, but you can do then the analytic continuation in the AMI.
Exactly. Because so this sum over Matsubara sum will be done by the AMI, and we'll be left with our external frequency, which we can continue. And at low order, it's actually not that big of a deal because you can take cutoff for these integrals and so on. But at higher order, like diagrams, it becomes, because you have one extra integrals per Green's function. So it's it actually costs you a lot of computation time. So the process is not to compute the self-energy on a k and momentum and frequency grid. So here is an example for second order self-energy, where we can see that the imaginary part is maximum on the Fermi surface with some distinction between the nodal and antinodal part already at this low order. And once we have this, we can actually interpolate the spectral function that results. So for example, we will go from something like this at 0th order and with a broadening that is frequency and momentum dependent, shown here for this is also second order calculation. So the first thing we can check is that we now have a calculation which is independent on the numerical broadening or the analytic continuation parameter, even though we now have two of such steps. The first step is when we compute the self-energy. So here we have a analytic continuation parameter that varies in the self-energy calculation itself. And you can see that the imaginary and real part of the current correlation do not change. And also in the calculation of the conductivity or the correlation function itself, changing the imaginary part of the frequency does not change qualitatively your result. You have, of course, sharpening of some features and so on, but that's much more well-behaved than what we had before. So we can now study the optical conductivity. So we did calculation for different temperatures for the current correlation, from which we extract the conductivity at finite frequency for now. And we can also look at the DC limit directly. And now, because we don't have this problem with the analytic continuation parameter, I can just take the omega going to 0 limit directly. Another advantages of the AMI tool is that analytically you would rewrite the DC limit by taking the derivative of the current correlation function. But because we have an analytical expression for this quantity for the real frequency omega, we can actually take analytically the derivative and evaluate directly this expression. So I think this is what you were mentioning in the bare expansion. If you vary your analytic continuation parameter, the derivative is going to infinity, so you have something that is problematic. This is after, for you it would be, you have taken the omega going to 0 limit, and then you look at the gamma going to 0 limit. And no, what if you reverse the order? I'm not sure what would happen, but.
So what order did you go now?
So this, for the bare, it's also a second order calculation, and for the even there I didn't mention. Sorry, this is just the 0th order. This is just the simple bubble.
Okay, so no vertex correction.
No.
Okay, got it.
And there's in the bold scheme, we have a well-defined answer for when the analytic continuation parameter goes to 0. So we can also study the temperature dependence of this DC conductivity, which is given here. And because, as I said, the evaluation does not depend on the interaction parameter, we can easily change the interaction and get a new answer here with a very cost-effective computation in a sense, because you just recompute the bubble in this case. If you want to study the frequency dependence of the conductivity, one popular way to do this is to rewrite the conductivity in an extended Drude model form, where you include a frequency-dependent scattering time and a frequency-dependent mass normalization. And this is widely used by also people doing experiments, so it's a relevant point of trying to understand what's going on. If you do this with our calculation, we get scattering time, where I've actually included a scaling here by the temperature, because you get the nice features that at low frequency, the scattering time actually scaled with temperature. So 1/tau scaled with 1/t. And then you have maximum of the scattering time, which is given somewhat by the bandwidth. And the mass normalization also have some structure in frequency with a finite value at omega going to 0. Yes.
This 1 over tau is just temperature. Is it right? Is this what you say?
The 1 over tau is the scattering time that enters in the
but
conductivity.
the smallest frequency, if it's always 2 point something.
No, so okay, here it's maybe 2 point something, but it will actually depend on the interaction.
I don't care about 2 point something, I care about it's just linear temperature.
Yes.
Is this a large temperature statement or?
Yes. If you look at the term at the beta, we are like above beta of 10, so it will be below beta of 10, so above temperature of 0.1, something like this. So it's still a very high temperature. It's not low temperature linearity resistivity or anything. But it's still okay, to me, surprising statement. And it's actually not so much a statement about the conductivity, I think, but because we, as I mentioned, we only compute the bubble diagram, it's actually a statement about the scaling of the self-energy itself, right? The scattering time should be given by the energy part of the self-energy. And if you plot the momentum integrated self-energy, you will see that you get the same scaling at omega equals 0. And overall the same. I mean, these two quantities are directly related. So now, of course, what we have done here is actually not much more evolved than what people have done before. In particular, calculating the bubble graph is what people do when they use the MFT, for example, to compute the Green's function and so on. So we now have two ways of actually going further. The first one and the most interesting one would be to include vertex correction. These have been shown to be relevant and important at high temperature, and also even with form of self-energies that are very local and so on. So they are really the effect of these terms on the final conductivity is non-trivial. However, for now, because this is a recent work, I don't have data for computation of the vertex correction. It's something that is ongoing. And what I can say is that there is actually no additional conceptual hurdle to doing this. It's just a computation game because, as I mentioned, the dimension of the integral actually grows very largely, especially when you use the spectral representation form. So this is still something that is ongoing, but what we have done is to include the fourth order self-energy in the normalization of the Green's function. And this is already something that could give us some interesting physics. Namely, it was shown that already at fourth order, you can get insulating behavior at the nodal or at the antinodal point, depending where you are, what is the interaction strength. And so you can get a metal to insulator transition type with a regime where the antinodal point is already has already an insulating behavior, but not the nodal point. So a crossover regime here. And just for reference, this is now something that you could not do like by yourself. Like at fourth order, there are like 12 diagrams, and this is like about 600 terms that you need to compute, analytic continue, and then evaluate. So the automation that comes with AMI and the fact that we store actually these expressions, this analytic expression is something that is important here already. So if you look at the fourth order self-energy for some range of parameters, you will see that there is actually a change of signs. And this is already something that causes us problem, mainly because here, for this value of interaction, you will still get a self-energy that is negative. So everything is well behaved. But if you actually increase interaction, you will see that at some point, the spectral function changes sign, which is here a sign that this perturbation expansion breakdown at some interaction strength.
So the reason is for this that your Monte Carlo sampling is just not respecting the causality, or why is this? Because your spectral representation should be just happy.
Yes. So the computation of the fourth order self-energy is correct in the sense, but what happens is because you have truncated the Dyson equation, you have some value. Okay, let me say it another way. If you were to compute the full series, you will get something that is causal and that is always negative for the imaginary part, for example. But because you have truncated your series, you get results that are not. You have some constellations that are missing.
I mean, which truncation do you mean? The perturbative truncation shouldn't violate causality, right?
I mean, if you truncate your self-energy expansion at some order, you. Okay, what is important?
In all diagrams of that order, I should be fine.
Yes, but then you have terms at higher orders that would cancel these contributions that are missing. And this is why at some interaction.
My hope, at least, is that a perturbation theory obeys causality on each order individually. And at least that would make me much more comfortable.
So actually, I've not seen this study for the self-energy in particular, but you can find other perturbation series where the results are actually diverging order by order. And so you actually need to take all order into account to get the right results, which is a convergence of the series.
Divergence is fine, but if it's causal.
Yeah, but what I mean is because you have divergent terms, if you truncate at some point, you will have constellations that are not occurring anymore. So in this case, it's related to this causality, but I don't think it's a causality problem. I don't know if I'm clear.
Okay. I'm scared now.
But okay, one thing to keep in mind is that as long as you don't go too high in interaction, this is actually fine. This is actually more a statement of your fourth order term being larger than your second order term. So in what sense your perturbation expansion is right at this interaction value is already questionable, I think.
My suspicion is this is a numerical issue. My deep hope is this is a numerical issue of your Monte Carlo evaluation of the momentum sum or something, and not that causality at the fourth order. If you stop at fourth order, but I have never done a fourth order calculation, so I know.
Shouldn't it be causal order by order?
That's what I said. Yeah.
Oh yeah, I will actually have to look. I don't know if other calculations have been done on the real frequency axis directly. That's I'm not aware of any of other calculations. So
the suspicion collectively now is order by order, which might help you a lot identifying or improving this.
Yeah. So the main thing is here the result is the result from the Monte Carlo integration is clearly positive. So this is and the question is if there is something that is missing, it's really a part of the phase space that is not sampled at all. So it's really.
So if I chose, for example, to live on a lattice that has only two momentum points, right? Then maybe you don't need to do Monte Carlo; you can just sum. And then my hope is this is going to be just fine.
Yeah, I understand what you mean. I would actually have to look more into this. For now, I will restrict myself to the case where everything is fine anyway, which is for lower interaction strength. And once again, I compute the current correlation and the conductivity within at zeroth order, so with the bubble diagram. And I can compare this to what I had at second order, for example. And one interesting thing is that because the scattering time is actually proportional to the imaginary part of the self-energy, if I rescale it by the interaction, I can actually observe what is the effect of this fourth order term. And you can see that we have like an increase of scattering at low frequency, like a weight transfer from high frequency to low frequency happening here. So To summarize what I've presented, algorithmic Matsubara integration is a technique that allows for the evaluation of diagrammatic series directly in real frequency, which is, I think, the main advantages it has over other diagrammatic technique. Here I've worked with a Hubbard model and Hubbard interaction, but you can possibly include frequency and momentum-dependent interaction of vertices. If you know an analytical form for it, so that it can be treated in the same way in the AMI. And we can also use spectral representation to include self-energy directly in the electronic unit function, for example, and get some sort of bold diagrammatic expansion. On the optical conductivity in the Hubbard model, I showed that the low-order perturbation expansion is controlled by the analytic condition parameter as a motivation to justify our renormalized perturbation approach, where we use a second-order or fourth-order self-energy to renormalize the electronic unit function, from which we get very well-behaved optical conductivity at zeroth order. I've shown this breakdown of the expansion, which remains to be discussed or to be investigated, and we can extract frequency-dependent scattering time and mass renormalization, which could be used to compare to other computation. Of course, this is ongoing work and very recent work, so there are a lot of things left to do. One thing which is our goal right now is to get the inclusion of the vertex corrections. So these second-order diagrams, which would hopefully have an important impact on the conductivity and get non-trivial results. We could also extend the study of the fourth-order self-energy in interaction and temperature, and to try to probe this metal insulator behavior that I mentioned. And of course, this is a 2D half-field Hubbard model, which is a very special particular case. We can extend away from half-fielding. We can include second-order hopping, and so on. Main difficulty is that the density is then a function of temperature and interaction itself. So you need to find the value of the chemical potential and so on if you want to stay at fixed density, but that's just that's not that difficult. More importantly, everything here is almost already ready to include the transverse component of the conductivity if you include magnetic field. And then you can start to address interesting questions such as this whole number or magnetoresistance and so on that have been widely studied in strongly correlated materials. And lastly, to finish, something that we are not really looking into right now, but that could be interesting. If some people know more about this, I would be happy to discuss. It's the use of force-force correlation function, which has been used to compute the current correlation function because the two are linked. But for some reason, in this bold diagrammatic scheme, the result seems very different, and we don't understand right now exactly why. And another thing that could be done, because what we have done so far is just using spectral representation, is to use another spectral function, such as one coming from the MFT or some dual fermion calculations to compare different physics, because the MFT will lead to is a strongly coupled technique from the get-go. Thank you.
Well, we're running over time, so unless there's a very quick question.
Very quick question. How is analytic consideration done in practice?
So it's actually, let me come back. What the MI will do, it will actually compute analytically all these terms, so do all the Matsubara integration. And then you can just take your Matsubara frequency here and replace it by a real part and some imaginary part, right? And you store this expression, and this will be what will be evaluated in your momentum integration afterwards. And this is also why we can take directly the derivative, for example, for the DC conductivity, because we have an analytic expression in the external frequency from which we can take the derivative and evaluate the derivative directly.
In your code, you presumably have to have a thing that knows how to convert Bose functions of energy plus the Matsubara into Fermi functions and vice versa.
Yes.
That was a code you put into the code.
Yes. Because otherwise the numerators will, well, if you don't do that and you do the analytic computation, the numerator will be,
Easy, yeah.
yes. And okay, the same way, here I only have a Hubbard interaction, but you could have some bosonic propagator if you know the analytic form, and then you would get Bose function, and everything should work exactly the same, at least.
Amazing.
For your sampling of a momenta, do you use the same types of Monte Carlo moves that I usually use for Hubbard model, or is it different mapping to some of these terms that you get on Matsubara?
Okay, that's a technical question. I'm not sure of the answer. I think it's a standard Monte Carlo sampling of the momentum space here, and your integrand is just because okay, there is a once you've done this step, you get so a lot of these terms, but like the sum over numerator divided by external frequency and so on. And there is a step of trying to reduce the number of terms and all this to have a nicer integrand in some sense. But then I think the Monte Carlo sampling is done on momentum in a standard way.
I mean, these are not independent momentum, or is it? I mean, what's the kind of domains of integration?
So here I have because we have this labeling scheme that will identify the independent momentum, right? And then it will write the non-independent one as combination of the like minimum set. So all of this should be independent momentum. So you are between 0 and 2 pi.
Okay, well, it means they're all in the real order.
Okay. Well, let's thank the speaker one last time. Andrew, what time do we resume?